All right, sorry about that. So let's get started. Welcome back from spring break. All of your final project groups are formed. So I think I only had to make one or two little adjustments. And so if you didn't hear from me, then the group went through fine. So I think as most of you know, there's a short kind of proposal assignment due this upcoming weekend. One page, maybe two, that just tells me the kind of system that you're interested in modeling, and shows me that you've put some thought into how you might start the modeling process. And so, show me some variables that might be in your model. So like, if you were modeling disease spread or something like that, then you probably would want to keep track of the number of people currently sick, the number of people who've been sick, those sorts of things. So like, what are the kind of quantitative variables that are going to go into your model? It'd be great if you want to throw in like a sort of high order causal loop diagram to sort of just, it doesn't have to do your whole model, but just to kind of show me that you've put some thought into how things might be related to each other. No stock and flow or anything. That's kind of what goes for the full project at the end. So that's kind of the first kind of deliverable. After that, we leave you alone for a while, and then we'll have in several lectures down the line, we'll have a class period where you're going to do a check-in with me, where during the class you'll kind of show me that you've got a minimal working model that is producing results that make sense, and you kind of get a check mark on that. And then after that, the next deliverable is just your final project report and your presentation, both of those that you'll upload online. So there is, in the final project module on Canvas, there's a little PowerPoint that kind of gives all the outlines of all the assignments that are due. There's also a video where I kind of go through that sort of mini lecture on what's expected for the final project. So if you have any questions about that, you can feel free to bring them up in class or email me or so on, but I'll just sort of give you kind of the timeline updates. And like the next deliverable due the end of this week is this sort of proposal. It's a group assignment, so only one person has to upload it, and it'll count for everybody in that group. So any questions about that moving forward? Let's see if there's any questions online. Yeah, I'm sorry. In the slide, the question was, are there any examples from past years? So I do projects in a lot of different classes, and so I don't remember everything I've posted on Canvas for each class, but there, I thought, but I might be confusing this with a different project class, is that in the module, I've got a sample from one of the previous semesters. If not, definitely for the little slides that I put together that are in that final project module, on like slide 2 or something like that, I've got some examples at the bottom, or I go through like a list of like things that you could possibly do. I can tell you as one example, last semester, I remember this, when toilet paper was sort of big in the news, a group modeled the dynamics of the kind of toilet paper supply chain, and kind of showed that there were variables that had to do with like inventory that was available for commercial, inventory available for retail. There were things involving people's sort of fear, and there were also like just generally how many people were working from home, how many people were working in the commercial space, or work from work. And then they modeled how all of those things, under certain parameter regimes, you could have major issues with toilet paper being undersupplied or being fine. So that's kind of one example of something that people have done. Yeah.
And we're presenting this, right? Like the class?
You're uploading. So I used to have people stand up here and we burn a class period, or depending on how large the class is, potentially 2 class periods, presenting to everybody. Now I've found it's a little more efficient. You're going to present, I think, and I forget that I think for this class I set it at 10 minutes, where you're going to upload a presentation, you record on however you'd like, let's say on Zoom, and you'll upload that. And you'll upload that on Wednesday, the last week of classes. And then everyone will have from Wednesday night to Saturday, you'll be randomly assigned one other group, their presentation, and a different group's report. And you'll just peer review that. And then so Saturday night, I'll have all of those. And then so in finals week, as I'm looking through grades, I will then review the final reports, the presentations, and the peer reviews. And I'll use the peer review scores as well as my own assessments to give the final grades on these reports. So you'll get credit for doing the peer review. And then the peer review from your peers as well as my assessment will be what goes on that. So that way you don't have to sit through everyone's presentations, but you're guaranteed that, probably in this class, 3 or 4 people will be seeing your presentation. So you get to watch one presentation and know that 3 or 4 other people have seen your whole presentation. Okay, any other questions about that? And then that works out well because I can then do stage 2 final exams. So I can do stage 1 the last week of class on that Thursday, stage 2 during finals week, and we can have a review session that Tuesday. So instead of the last week of class where one lecture is burned on just presenting to the whole class, where it's maybe interesting at first, but maybe gets a little long towards 4:15. It's kind of I try to strike like a balance of that and then make better use of that time. So that's the structure there. All right, any questions online? Okay, good. Okay, so yeah, we talked last time about lookup tables and converters. So if you weren't around for that, that's recorded. So these were 2 structures that help make more realistic relationships among things. We're going to be using lookup tables again today. So are there any questions about how lookup tables or converters work? Your first, so there's I think assignment E2. The first question of assignment E2 is you have to, I think, use a lookup table. So everybody's going to get practice in building these things. Okay. All right, so today our big focus is on delays. And so far we've talked about stock and flow diagrams where there's an immediate response. So if one variable changes, the other variable feels that change immediately. But we know in real systems, there are these delays. And so when you've got hunger, and immediately when you're hungry, you might start eating. But when you eat, you don't necessarily immediately relieve that hunger. And so the amount of this delay can greatly change how much someone eats. If there wasn't any delay here, then once you'd start eating a little bit, then you might immediately relieve your hunger and stop eating. And so the delay here, getting it right, it was really important to model the true amount of food that someone's actually going to eat. So we need to figure out how to properly model these delays inside Vensim and Insight Maker. So if we focus on these delays, we have to think about what are sort of the causal factors that go into delays? What causes delays? And we're going to find that there are multiple types of delays, fixed delays and smoothing delays, that we're going to be talking about today. And so once we've identified those 2 different types, fixed delays and smoothing delays, we're going to learn about the 2 different ways that you simulate those types inside Vensim and Insight Maker. So let's talk about fixed delays here. So when we talk about fixed delays, in this system of the hunger regulation system, this is like the time it takes from food to get from the mouth to the stomach. It's a fixed delay. Basically, food travels roughly at constant velocity down your esophagus. And so if food enters your mouth at time t, it's going to enter your stomach at time t plus some fixed delay. And it doesn't matter how much food it is or anything about the food, it's always going to be that fixed delay. It's like a constant offset there. So that's what we refer to as a fixed delay, a fixed amount of time to go from one point to another. So it's the simplest form of a delay. And so in Vensim, there is a function which implements a fixed delay pretty simply. So let's take a look at that. So if I've got this simple diagram here, it's not even a stock and flow diagram, it's a little contrived. So I've got this time shadow variable that is going to drive this ingestion rate, which is going to be sort of like when the food enters the mouth. And I'm going to then model this rate in the stomach. We're going to see that this the rate that food enters the stomach is just going to be a delayed version of the rate that the food enters the mouth. So if I look into this ingestion rate, I am going to build a lookup table here. So we've already seen this. So if I look at this ingestion rate, I'm going to configure this as an auxiliary subtype with lookup. I'm going to make its input this time shadow variable. And then I'm going to go into the graph here. And then I'm going to go down here into this lookup table. And now I can put a signal here, which basically goes from my simulation start to my simulation end. And this sort of simulates the history of food ingestion in this simulated model. So this is saying that this simulated person doesn't eat anything, but then at time, looks like I've got here at time 5, they eat 5 units, whatever that means. And they continue to eat sort of that 5-unit rate until time 6. And then at time 6, it drops back down to 0. So that's what we're seeing here. So if I hit play on this sim, then this ingestion rate, if I were to graph it, at time 0, it would look like this. At time 5, it would jump up. At time 6, it jump back down. So that's all that I've implemented here. No delays yet. They're just generating kind of a sample of food ingestion signal there. So then if I go over into the stomach formula, then I've got ingestion rate as my variable that is going into the stomach here. So I just configure this as a normal auxiliary variable with an expression. And it's going to take ingestion rate as an input, and it has this function delay fixed. And so delay fixed is the function in Vensim for fixed delays. And so it just takes the variable you want this to be the delayed version of. You want the magnitude of the delay, so in this case 5 seconds, and then it takes an initial condition. And the reason it needs this is when you start the simulation, this delayed thing doesn't have any input, because if it's a delayed, if it's 5 seconds delayed version of the ingestion rate doesn't exist before time 0. So we don't have anything to delay. So we have to say, well, what is it initially before the simulation finally catches up to the 5 seconds? And so we're going to say it's initially 0. So the rate here will start at 0, and then once it hits 5 seconds, at 5 seconds, the rate into stomach will be whatever ingestion rate was at time 0. And otherwise, will be just a copy of that. And so this is how we implement a fixed delay in Arena. And so if I then plot this, if I hit play, and then I go and I graph the ingestion rate as well as the rate into stomach, and I've got this graph down here. The ingestion rate's the blue one, the rate into stomach is the red one. And you can see that the rate into stomach is an exact copy of the ingestion rate. So whatever signal shows up at the ingestion rate, this one right here, 5 seconds later, the exact same signal shows up right here. That's how I implement a fixed delay in Vensim. So I can just hide there. There's a 5-second delay there. So, so any questions about that? Does that make sense? Is it's just a way for me to generate these delays. Now, the next thing I want to show is how to incorporate this into a stock and flow diagram. So questions about this basic idea here first, before we make things a little more complicated by adding stocks and flows. Yeah. So the question was, how do you decide on 5 seconds? How do you decide on how long the delay should be? And that's an excellent modeling question. And so, so we have to come up with a justification for why 5. So I might have to go and ask a physiologist or somebody, somebody who studies, these processes, and say, on average, how long does it take for a bolus to travel down the esophagus? And if they said, well, it usually takes this many centimeters per second, and the average esophagus is this long, then you could say, on average, it's going to take 2 seconds for food to get from mouth to down to stomach. So it's a very application specific thing. I'm going to show you another example in traffic where you might imagine, if I know the average speed of cars on the road, let's say you assume the speed limit on city roads, then if I know how long the road is, then I could say, well, on average, it's going to take the speed limit times the distance, or maybe divided by, or maybe I got that distance divided by speed, and that would give me my average delay to get from one block to another. So it kind of depends. Other questions? Does that make sense? I see that makes sense online. All right, so this is with this kind of contrived example where these two variables, let's put it into a stock and flow diagram. So this is a more realistic model of what's going on inside the mouth and the stomach. I mean, not that much more realistic, but more than the last one. So the idea here is I now have 2 stocks. This is the amount of food in the esophagus at any instant of time. And this is the amount of food in the stomach at any instant of time. So the idea here is if I have an ingestion rate, this is the rate at which food is entering the mouth. then if nothing was exiting the mouth, then you'd imagine that it would just accumulate in the mouth. And so a constant ingestion rate would cause a ramp in the food that's, a constant ingestion rate into the esophagus would cause a ramp up of food into the esophagus, where there'd be none initially, and then it would ramp up, and then there would be, a gradually accumulating version. But eventually that food has an outflow into the stomach. And so that outflow is going to reduce the amount of food in the esophagus. And so that's why we create these stocks and flows, is at any instant of time, we can ask how much food is in these containers. The esophagus is a container, the stomach is a container. And that's kind of what we've modeled here. So with that, we can then take those ingestion rates and turn them into these flows. And so what I've got here is the same ingestion rate as I had on the previous slide, but now my delayed rate into stomach is modeled as an outflow from food in the esophagus and an inflow into food in the stomach. And so by doing that, if I now plot these things, then I've got a lot more to plot on here. I've got the green line, this green box here, that is the ingestion rate. Now I've got food in esophagus, that's the blue line. And like I was saying before, the green line is constant from time 5 to time 6. And that's what causes the esophagus food to kind of ramp up to some finite amount. And at the point where food stops being inserted in the mouth, the food in the esophagus stays constant. Now it stays constant while the food is moving down the esophagus. It doesn't actually dump out of the esophagus until it hits the stomach. And that is that fixed delay. So 5 seconds later, this ingestion rate gets mimicked as an outflow out of the esophagus into the stomach. And that's why you see this cross here. Now you're seeing food get dumped out of the esophagus. And as it gets dumped out of the esophagus, conservation of matter, it gets ramped up in the stomach. And now all that food is in the stomach and no food is in the esophagus. So that's how we model this dynamic process of things kind of moving in a stepwise fashion through a system over continuous time. Okay. So I see a question online. Is this the same as respiration rate of plant versus seasonal carbon emission and plant biology? There are a bunch of different systems you might model this way. If you understand the physiological process as one that involves a fixed delay, usually transport, I'll list a bunch of fixed delays here in just a second, but transport delays are typically viewed as fixed delays. So the amount of time to get from the water, in order to get the water to get from the roots up to the leaves, that might be a transport delay, and that could be modeled this way. And you could come up with a lot of other transport delays. Okay, so any questions about this example? All right, so I want to show you how to do this in Insight Maker, almost the same exact deal. So in Insight Maker, we can create our lookup table for my ingestion rate, just like I did before, with time as an input and my rate into stomach. So I go into my lookup table, I make sure I set its input to time. So we don't use a shadow variable here, it's just a part of the lookup table. I build the same lookup table here. If the interpolation set to none, then if I cause it to go at time 1, it goes up to 1, and at time 2, it goes down to 0. So I only have to put that those 2 points there. I don't have to like specify all of the corners of that rectangle. It naturally holds that for me. So I get the same ingestion rate pulse. And then for rate into stomach, and so when I say that same ingestion rate pulse, in Insight Maker, I also can, instead, if I don't like doing it the lookup table way, there's a nice function called pulse, which will do it for me without the lookup table. And so what you can do with pulse is I can say, I want a pulse that starts at a particular time, goes to a particular height, lasts for a particular duration, and maybe repeats or not. So in this case, I'm saying it doesn't repeat. So I can put this pulse in as 1110, which means start at time 1, has a height of 1, lasts for a duration of 1, and doesn't ever repeat. And this gives me the exact same pulse as that converter gave me. So that's another way that I can generate these input signals. This is sort of bonus information. And if you like that implementation, you can actually do that in Vensim as well. So this is what I'm saying. Vensim has this, so it has a pulse train function, which I could have used as well. Okay, so, but the big thing is this delay. Well, how do I do fixed delays in Insight Maker? Well, there's a delay function. just like Vensim, but instead of being called delayed fixed, it's just called delay. I say what I want to be delayed. I say how much of a delay, and again, the initial condition. Exactly the same as in Vensim. And so with that, I get exactly the same output that I saw in Vensim. And if I want to then 5-second delay. So then if I want to do the same thing with stocks and flows, I put my stocks up there, do exactly the same thing I did in Vensim. My outflow here, outflow from esophagus, inflow to stomach is the delayed ingestion rate. And if I do that, I get exactly the same output that I had in Vensim once again. So that's how to do it in Insight Maker. Pretty much the same as the way you do in Vensim. So these are examples of fixed delays, schooling behavior. So whenever you have tight clusters of individuals that move together, you could think of this as fish, or you could think of this as people getting on a train. So somebody all gets on a train car, and then they'll stay in that train car. Then that train moves at a particular speed down the tracks and then lets them all off. Well, that's a fixed delay. So that's kind of like they're schooling like fish together. Age structure and populations. So you might say, we want to model the effect of some change in educational policy that is implemented in grade 1. Well, you know that students in grade 1 become students in grade 2, become students in grade 3, and so on. So whatever the effect that happened in grade 1, you're going to then see in grade 2 students the next year, and grade 3 students the next year, and so on. So modeling these age-structured populations is another place where you put these fixed delays. Like I say, students moving through a school, and then I've talked about transit delays as well. So things moving down an esophagus, things moving through pipes, and so on. These are all examples of fixed delays. And we'll contrast that with smoothing delays, which are a little more sophisticated next. All right, so any questions about this, about the fixed delays and how to implement them? Questions online? Okay. All right, so let's do a mid-class attendance exercise. Haven't done one of those in a while. So I'll put the link in the chat, give everybody in class a chance to queue up here. And so maybe this question will be, give a brief example of a fixed delay. So I just mentioned a couple of them. You know, you could use the exact same example that we worked on in the last couple of slides here. Just give me an example of a system that has a fixed delay. And again, if you don't get it in class, of course, you usually have 24 hours. I actually gave everybody overall a spring break to the attendance exercise for lecture E1. So, okay. All right, so fixed delays. The example we've been doing working so far is this kind of hunger problem. But if we really think about the delay that we care about in hunger regulation, it's probably not the 2-second delay it takes for food to get from the top of my throat to the bottom of my throat. That's probably not the delay that's really limiting me from satiating my hunger. So what is the delay that matters? Well, if we think about it, it's really what's going on down in the stomach. And that's what we refer to as a smoothing delay or an average delay. So if you think about it, food hits your stomach, some nutrients will almost immediately enter your bloodstream, but some of them are going to need to digest for longer. And so what happens is, so this blue curve, this is kind of like food entering your stomach, and this red curve is like nutrients entering your bloodstream. And so you're going to see that as the food enters your stomach, the nutrients slowly rise up in your bloodstream. And as the food exits your stomach, there might be still some nutrients that's sitting around in your gastric acids that are going to continue to be absorbed into your bloodstream. So, your bloodstream still feels these nutrients. It takes a while for them to sort of decay off. So this is what we refer to as a smoothing delay, where you don't get immediate access to whatever the new thing is. You kind of have this sluggish access where it smooths the edge out. It kind of it filters off this edge up here, so that you have to wait a while to get up to the maximum, but you do get some access to it initially. So, so this is kind of like, probably the delay that's more important in this hunger loop, where the output changes more sluggishly. You've seen this before. This is exactly like the toilet flow example, where we kind of desire the toilet to be immediately full, but we know that we can't just dump that much water into the back of the toilet instantaneously. The valve has to fill it up gradually. And so the sluggishness of the valve means that the toilet water, as you've simulated, starts at 0 and it sluggishly grows up until it hopefully rounds off at our desired level. So that is considered a smoothing delay of the input signal, which is that flush. So the input is the handle, the output is the water level, and that's a smoothing delay is what relates the two of them together. Sometimes we refer to these delays also as exponential delays, exponential damping, exponential decays. You can kind of see that decay language in the back end here, where you can see that as the input dies off, then the water actually in there falls off slowly. So this would be kind of like when you actually flush the toilet when it's full and the water goes into the tank, then some of that water might go through very quickly, the rest of it might not, and so you might get a little bit of like this is the tank water as it's filling the bowl, as kind of maybe an example there. So this is an example of a smoothing delay. So we have this parameter that for now I'm going to call delay, which characterizes the sluggishness, but it's a little tricky because in a fixed delay, I can actually say it takes 2 seconds to get from here to here. But this is like the average delay for like a marginal unit of thing that's in the system moving around. So in the nutrients in the bloodstream, some of those nutrients get in the bloodstream immediately, but some of them take a while. So we can say on average, how long does it take for nutrients to get into the bloodstream? And that average delay is what we're going to call the delay here for smoothing delay. It's the average delay for the whole process. So, so that's this delay that we have to characterize here. So if I wanted to model this, so there's going to be a shortcut here, which is why I'm going to go through this kind of quickly, because we'll end up using the shortcuts. But the basic thing here is that you can build this averaging system, which is itself like a stock and flow. It's kind of like your stomach itself needs to be built with another stock that represents this change in the nutrients that are entering the blood flow at every time. So it's kind of like we can view the food entering the stomach as an input to this kind of toilet tank, which is the nutrients entering the bloodstream. And this delay, which is this average delay, just like we implemented the toilet tank, is just going to be our target, which is like the food in the stomach, like how much we want this is the stuff we want in the bloodstream, minus the amount that's actually in the bloodstream, divided by this sluggishness parameter we're calling delay. So this is our average delay. So in the toilet tank example, it's like the average amount of time a small bit of water takes to get into the toilet. So some gets in fast, some gets in very slow. On average, across all of those like little marginal bits of water, this is the average delay. And that's kind of what we mean by delay here. So, so this, and we call this an averaging delay because we can view the output as kind of this, is this sort of averaged version of the input. So the input is sort of instantaneous. And if we think of a time average, we can think of this is sort of like the average input over time. Like if you imagine a time window of like 5 seconds long, as it sweeps along the input, then for a while it's just 0. And then suddenly that leading edge comes into the window. And as the window gets farther and farther along, that leading edge becomes more and more of the whole window. So it's like we're averaging the past state of the stomach with the future state of the stomach together. And that's where we get this term averaging delay. And so that maybe I'll make more clear here in a second here. So this is me just sort of, I think, indicating pictorially all the things I've sort of said already, relating this to our toilet tank example, where we've seen smoothing delays. We've implemented these ourselves. It's part of the reason I had you do the toilet tank example was so you could build a smoothing delay with all the parts yourself. Now, as I'm about to show you in Vensim and Insight Maker, they have a module that does all of this for you behind the scenes. You don't have to build one of these systems every time you want a smoothing delay. So that's what we're going to get here. All right, so again, I just want to get into why we call it averaging delay. If I were to take this model here I could redraw it. So this is your toilet tank model here. I could have redrawn it over here as kind of a toilet tank where I've got an outflow, but it's not like a leak outflow. It's just redrawing the exact same formulas. Because I have a minus in the inflow here, I've decided to take that and split it up so that I've got the positive term on the inflow side and the negative term on the outflow side. And this stock and flow diagram, you can write, if you were to write out like how to build this in Excel, as a formula that looks like this one. So when we were simulating everything in Excel, we said the next stock value is the previous stock value plus all the inflows minus all the outflows times dt. So this is exactly what we were doing in Excel. So this is showing how to get from one row to another. So this diagram, if you were to write in Excel, would look like this. And the reason I'm bringing that up is it allows us to kind of analyze what's going on here, because this I can sort of play with by rearranging the terms. Just algebraically, I can factor out a couple of different things. So this average shows up in two places, so I can factor it out, and that begins a 1 minus dt over delay. This thing doesn't have an average, so it just gets the dt over delay over here. And so what I see with this is I actually see that the current value of the, say, nutrients in the bloodstream is an average of the previous value of the nutrients in the bloodstream plus the food that has entered the stomach. And so it's like a weighted average of these two quantities, the past and the future. So that's what we mean by it's a smoothing delays or averaging delays. We're somehow allowing the past to have inertia to carry into the future. And we can control how influential the past is by adjusting the amount of the delay. And so if I have very large delays, then I think that's what I've got here. In the no delay case, so when I have delay is equal to dt, so it's like instant. So the next row so I don't wait any more than one row. Then when delay is equal to dt, this past term goes away because this just becomes 1 minus 1. But this future term just becomes input. So in the no delay case, when you said delay is equal to dt, the smallest time unit in your simulation, then the nutrients in the bloodstream equal exactly the food in the stomach, maybe delayed by 1 time step, but the time steps are super small. So this is what I mean by kind of a no delay case. If I go the other way, where I've got like infinite delay, then this dt over delay goes away, and this just becomes a 1. And this dt over delay goes away, and the future nutrients in the bloodstream is equal to the past nutrients in the bloodstream with no input from the stomach. And so that's kind of what we mean by as we shift the delay from 0 to infinity, what we're really doing is changing the influence of the input on the trajectory of the system. So the past becomes more important as we make the delay longer. The past becomes less important as we make the delay shorter. And that's why we call it the averaging delay. Okay, so is that, I think I've got, yeah. So does that make, are there any questions about that? So this is just conceptually why we've got these different terms for it. We call it smoothing delays because they smooth out these hard edges. We call them averaging delays because a smoothing delay is a weighted average of the past value of the variable and the future values that we kind of want the variable to be. And that's what causes it to smooth out, this inertia that we've added to the system. Okay, questions online. So they say, what equation is more efficient? So online, there's a question about very specific to carbon respiration. And so so that I think we should probably take offline because there's a bunch of different ways you can model things that have to do with photosynthesis and carbon respiration and so on. So, but most physical processes have this kind of smoothing delay approach. So transport delays are definitely common, but when we get into physiological processes, then there's very often it's more the smoothing delay. And then you have to choose the delay that makes the most sense for your system, which kind of goes back to that question from earlier. And we'll get into that in just a second. Because we actually already know how to choose these delays. We talked about it in the toilet model example. So yeah, so I mentioned the delay is kind of the average delay. Delay is an average time a small fraction of food stays in the stomach. It's another way we can conceptualize this. So all these kind of examples that I've given here. So you can also view the delay as like the mean lifetime for systems that behave this way. So if you were to think about food in the stomach, as it exits the stomach, as it's sort of dying off, you could say, what's the average lifetime it spends in the stomach? Well, that average lifetime that it spends in the stomach is this delay parameter. So these are all ways that we can conceptualize this funny delay that's in these smoothing delays. And in general, I've used this term inertia a bunch of different times. And where that comes from is this idea of smoothing delay is like, comes from sort of, it's like physically embodied. So if you go back to thinking about physics, you've got Newton's second law, force is equal to mass times acceleration, F equals ma. And if we think, so another way to say that is a net force, so this is like, I apply this much force to an object, produces a proportional acceleration in the direction of that force. And this mass is the proportionality constant. So what this is really saying is the input is force, the output is acceleration, and how sluggish the system is mass. If it's a really heavy object, if I push on it hard, it's not going to move very fast. If it's a light object and I push on it with the same amount, it'll really get going. So mass is like a proportionality constant. It's a proportionality constant that Newton sort of came up with to represent the relationship between an input and an output, between force and acceleration. So with that, we can do a little bit of rearrangement, and we can say, well, F equals ma, that's Newton's second law. I know that acceleration is just the rate of change of velocity. So you know, this is like, acceleration is kind of like the flow into the velocity stock. And so I can play with that a little bit. I just move the velocity to the other side. And what I see here is that the flow into the velocity stock is just equal to this F, which is kind of like an input, divided down by the mass. So we're going to see this is going to relate to one of those, the function that we just recently saw that kind of characterizes smoothing delay. So I write that in words. The change in velocity is the force of the change divided down by the mass. And I can say more generically, the change in a system variable is the force of that change divided by the system's inertia. So we will often talk abstractly about systems that have lots of inertia, even if they're not physical systems. We can say that people's, if somebody, and I'll list a couple of examples here, if someone's really stubborn and they don't want to adopt a new idea, we might say that there's a lot of inertia, which means that you need to apply a whole lot of force to convince someone to change their mind. So we often use this idea of mass analogously as kind of a model in thinking about how people have resistance to change. And this becomes really important in sustainability problems, because we're oftentimes talking about sustainability problems, how reasonable it is to ask someone to change their behaviors. And so someone who has sort of low inertia is going to be easier to change than someone with high inertia. And so we can model how resistant they are by changing something that's equivalent to mass. So a system's inertia causes the desired state. So we want someone to change their mind immediately, but it takes them a long time to change their mind. And the mass in our model system represents how long it takes for this smooth version of someone changing their mind to whether it takes a really long time for it to finally hit the target, or whether it rises very quickly. So if you have a lot of mass, this will take a very long time. If you have very little mass or very little inertia, it'll rise very quickly. So that's what we mean when we talk about the inertia in these systems. So instead of using mass in these systems, we're just going to characterize the time it takes for this to happen, and more refer to that maybe as like delay length or time constant, which we've already heard before. And so we're not going to actually need to come up with a mass of a society, but we can talk about how long it takes for certain groups to adopt a change versus others. And that time is effectively the exact same thing as talking about mass in physical systems. So yeah, mass is our physical constant there. So examples of this kind of analogy here. So we know that mass prevents instantaneous changes in velocity. The more massive you are, the harder it is to change velocity. fun fact, if the only objects that have no mass are objects that travel at the speed of light. So photons have no mass, they travel the speed of light. So you can't really slow a photon down, but it's kind of like this idea that if you were to try to speed anything else up to the speed of light, then the more massive they are, the harder and harder it's to get there. But the one thing that has no mass is automatically traveling at the speed limit. Heat capacity. So if you've heard this term, it's a term that represents, as you heat something up, how quickly will its temperature change. So, you heat up a pot of water on the stove, it doesn't immediately get, even though you turn the stove on, it doesn't immediately increase its temperature. We represent the relationship between the heat that you've added and the temperature over time with this thing called heat capacity. So, and it works exactly like mass. Bucket diameter. So if we trickle water into a bucket, the bigger the bucket, the slower it is for the height of the water to accumulate. A small bucket or a graduated cylinder or something like that with a small trickle, very quickly the height will change. But a fat bucket with a trickle, the height won't change very fast. So even the diameter of the geometric parameter can act as a sluggishness parameter, as an inertia parameter. And then stubbornness, I mentioned this already. You can model different groups of people and how likely they are to change their mind. Maybe somebody who's very naive is sort of the opposite of somebody who's very stubborn, where you tell them anything and they immediately change their mind. They're kind of like the photon, always traveling at the speed limit. But if someone else is really fixed in the way that they believe, then we view them as a high inertia system. So they have a high sluggishness and so on. So these are all kind of analogous systems here that we can model mathematically with the exact same formulas in your system. So this is how we come under that. And they're all going to kind of look like this. You're going to build a stock that is going to represent like someone's opinion on climate change or whatever. And then you could say their change in the flow into that stock, the rate of change into that stock is going to be equal to the thing trying to make them change their mind divided by this parameter, which will be this delay constant that we're talking about. So if they have a very long delay, then it'll divide down that change so that you get hardly any change in the stock. If they have a very small inertia, then it'll make it them change much more quickly. So this is all I'm kind of saying here. It's all F equals MA. And that's all that we've kind of like, that's what this system, the toilet model system is. That is it, just basically saying, like, when we think about people's stubbornness to change, we model it identically to where you model the toilet, where you can think that the valve, how quickly that valve opens, is related to sort of how quickly people can change their mind. And so we would mathematically model them with exactly the same expressions. We would just interpret the expressions differently. In some cases, it's water. In other cases, it's how quickly they adopt to change, as an example. So delay is just a way of us characterizing how quickly these systems rise. All right, so that's what I mean by smoothing delays. So before I ask for questions here, I want to just contrast smoothing and fixed delays in a concrete, no pun intended, example from traffic. And so the idea here is I've got cars that are waiting at an intersection at, say, intersection A's light. And then there's going to then, imagine that light changes from red to green. Well, then cars will start streaming into this block between intersection A and intersection B. And then eventually they'll stop at intersection B or go through intersection B. So I'm just really focusing on intersection A and the distance between intersection A and B. Now, right after the light goes from red to green, then it's kind of like from a traffic engineering point of view, we want everybody to get into the interstitial space in between the intersections. We want them to move. But we know that they can't all move instantaneously. You're going to get the cars in front are going to move immediately. The cars behind them are then going to start moving. And then behind them are going to start moving. So you're going to slowly fill up this space in between the intersections. And that's what we model as a smoothing delay. So we can model that time one, that's when the light changes from red to green. And so we desire that all the cars get into this block between the intersections. But In reality, it's very slow for cars to fill up that. It's kind of exactly like the esophagus example. So you get some that come in and then others, and then gradually they sort of fill up this space in between. Now, once any car enters the intersection, at that point, we assume they're at their kind of terminal speed, and they're just going to travel at that terminal speed all the way down the intersection. So if we want to model who's coming into that intersection, at intersection B, then we use a fixed delay. And so the idea there is that if I get one car entering the intersection right over here, right after intersection A, then we know that that one car is going to enter intersection B exactly, I don't know, 10 seconds or whatever later. And so that's kind of a fixed delay. So I can put both of those in a simulation together. If I'm trying to simulate the average traffic flow through a city system, I can have a bunch of these stocks, which represent the number of cars currently stopped at an intersection, the number of cars traveling between intersections, and so on. And all these things can interact with each other. And I know the kind of physical processes that get things from intersection into the block are going to be smoothing delays, and then across the blocks are going to be fixed delays. So that's a contrast there between smoothing and fixed delays. Okay, so that's kind of the key differences between these two, fixed and smoothing delays. So before we get into sort of a little bit more of the details here, are there questions about these two delays, and how they differ, and the meanings of these things? Any questions online? Okay. All right. Okay, so I mentioned that this is kind of, this would be a pain if we had to build these things every time. We had to build the toilet tank example every time we wanted to use a smoothing delay. So how do we take a shortcut of that inside Vensim and Insight Maker? So if I look inside Vensim, there is already a kind of toilet tank delay built. In other words, the entire toilet tank example has already been implemented in one block in Vensim. So, and the way that looks is I can create wherever I want a smoothed version of another input. I create, in that flow variable or in that auxiliary variable, it's got inputs coming into it, and I can use the function smooth. And smooth takes two parameters, the input that's coming in there, and it takes then the delay. So the average delay, basically, for this smoothing delay. So I create a variable like this kind of circle here, or imagine this to be a flow, and it's going to take as an input the delay, or the whatever I want the delayed version to be, and then I've got the amount of delay as well, and then I just dump that into this. And so if I was re-implementing the toilet tank model, I could make my input just a constant 15, because I want it just be a constant value 15 across the whole sim, and the initial value of this delay is going to be 0. Then this delay here, I can make it equal to 1 if I want to match your toilet tank example, because we just assumed that the relationship between the tank gap and the flow rate was like a unit proportionality. But if you want to slow it down, you can make this delay higher. If you want to speed it up, you can make this delay lower. And this function here, smooth input delay, like basically smooth 15,1, that will implement the toilet tank model that you guys did in that homework, all in just one function there. So that's how we can do it in Vensim there. So here's an example. I've got an input, which it could be a constant, again, in the toilet tank example, or this could be a variable as well. And then then I've got my delay. So this will be a smooth version where the delay in that smoothing will be 2.5 seconds. And so I end up getting an output, just like your toilet tank model output over here, where the input jumps up at a particular time and the output sluggishly follows behind it. So that's how we do a quick shortcut in Vensim. That's just that other example there. Likewise, it's the toilet tank and so on. We refer to this in dynamical systems as a step response. And so whenever you put a unit step into a system as an input, so that's what I refer to here as this input. When I go from 0 to 1, on an input, and then I watch how quickly the output changes. We know that the output for most systems will eventually reach the input, but we just don't know how quickly it'll go up to there. And we refer to that as a step response. Now, what we do with step responses is we use them to measure this time constant that we've already talked about before. So this is this magic number, 63.21%. I can measure how quickly the system rises to 63.21% of its total, and that will be the average delay for the system. So for this one here, I know that it's 2.5, and sure enough, it reaches 63.2% of its rise in 2.5 seconds from when it started. And so that is our so-called time constant. So how do we do that? This now provides us a way to go from physical systems into our models. So there's the question earlier, how do you choose the delay in a fixed delay system? This is how you choose a delay in a smoothing system. If you think your system is governed by a smoothing delay, then in the real physical system, you try to put in a step response here. So, like traffic goes from red to green. You look for data where the intersection or where the block after the traffic light is empty. And then you look for data where traffic goes from red to green, and then you watch how quickly cars get into the intersection. And then you use that data to figure out the average speed of the cars as they enter the intersection. And it will be this 63.2% number. So that's this time constant that we've already talked about. Okay, so questions about this step response. Again, it's sort of, we've already seen this with the toilet tank example. This is just kind of just reinforcing how we go from data to actually picking numbers that we put into our model. All right, so for maybe this other attendance exercise, and let's try to solve this problem. I'll put this in the chat as well. And so the question here is, so I've got a step that occurs at time 1, that's the green line, occurs down here at time 1, jumps up to 1 here, and then I've got this blue line that starts rising. And if I'm assuming this is just a smoothing function, then what would be approximately the time constant of this system? So, so it's maybe hard to see, but this is 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%. So every tick on the vertical axis is 10%. So if you're looking at this, then you can sort of, and then down at the bottom, every tick on the horizontal axis is a single unit. So 0, 1, 2, etc. So given that the time, given that it started rising at 1, what is the time constant of this system? So I'll let you guys put in that as your answer. And then as you're doing that, does anybody have a guess? And you can put a guess in the chat if you're online, or if you want to raise your hand in person here. What if I showed you these data and I said, build a system that models this in Vensim, what would you put as your smoothing delay? What is the time constant of this system? Any thoughts? Remember, the hint is you take that magic percentage that I talked about and you ask, at what time does the system hit that magic percentage? So any guesses, roughly speaking, where the time constant of this system should be? I see a questions online here. So I hear you said about 3 or 4 seconds. So how many people agree with 3 or 4 seconds as the time constant for this system? Online, someone else said, so I see online, I see someone say 2. Online, someone else says 3. I see a 2.7. So if I were to kind of, I'm not going to point here because it's a little bit funny. So how many people would say the time constant is around 1 second? How many people would say 2? See several hands. How many people say 3? Several more hands. 4, 5 or greater. Okay, so the trick here is that, if I remember, the hint here is that 63.21% is the number we're looking at here. So I hear some realizations in class here. So just for those, so if I put a pin up here, I'm gonna draw 63% or so, and that hits about here. And then that shows that I come down and I look at this point here. Now, I'm tempted to say the time constant is 3 at this point, but I have to remember the step started at 1. And so the actual time constant of this system is 2. So it's the difference between 1 and 3. So if I showed you data like this, you now could go in and in your model, you'd be able to calibrate your model to match the time of this real system. Any questions about that? I'm sure if you've got questions, other people have got questions too. So I can maybe write this is 63% up here. All right, does that make sense? Everybody do you feel good about this? Okay. Okay, good. All right, so that's how we pick these for the smoothing delays. So we can also do the same game in Insight Maker. So again, don't have to draw this ugly thing in Insight Maker. Insight Maker has got its own module to do this, maybe not surprisingly. So in Insight Maker, if I create a variable or a flow, I can go into its equations, and it's got its own smooth equation. And it's very similar to Vensim's. It takes an input parameter, the thing that I want this to be a delayed copy of, the average delay, and whatever the initial value is, again, to sort of where it starts before it has data to start generating this. And so this initial value is optional. Otherwise, if you don't put anything there, it matches whatever the input was at its kind of initial value. So, so I'm just kind of stepping through this. So this idea here is that I can do the exact same thing I did in Vensim, where if I hook this thing up, if I have some signal here, which is like a step response, I could put whatever 2.5 is my delay, come in here where I have my signal and my delay. And then if I simulate this thing, I get the same thing out, just like the toilet tank example. So basically built exactly the same as in Vensim. So input changes instantaneously, output changes more sluggishly. So that's how we do it in Insight Maker. Pretty much the same. You learn one, you can easily do it in the other. Okay. All right, so let's get a little more advanced. So any questions about that? You'll have some, I think, experience, if I remember correctly, working with delays for, I think, question 2 of that assignment E2. All right, so some more kind of related and more advanced topics here that are related to this. I mentioned step responses are very popular in dynamical systems modeling because we like to characterize things like time constants and then test to see if we got the right thing. So we can generate steps, just like in a real world, we can generate a step response. So, so as an example, if I had a little solar cell or something like that was sitting here in the room, I could turn off all the lights in the room, let the solar cell kind of decay out, and then turn on the lights in the room, and then watch maybe the voltage on a battery that the solar cell was charging. And that would rise up in this kind of this delayed fashion. And I could say, how fast does this solar cell charge this battery? And I could use the time constant to characterize that. Kind of an example of a physical way for me to generate a step response. Turning on the lights is like generating a step. I can generate steps inside Vensim and Insight Maker using the function step, where I can say the height of the step and the time I want the step to be applied. Similarly here in Insight Maker, it's flipped, where you do the time first and the height second. So always check your syntax before you implement these things, and you can generate these signals, these steps inside Insight Maker in Vensim. So here I've generated a step at time 1, going up to height 1. And the other things that Insight Maker and Vensim give us are what we refer to as higher order smoothing functions. So sometimes I want a sluggish system, but I might want it to sort of rise in a slightly different way than a standard first order toilet tank smoothing system. And so what these higher order smoothing, I've kind of tried to summarize it down here. What I mean by a higher order smoothing function is, imagine chaining together smoothing functions where, like, if I want to chain 3 of them together, each little smoothing function is going to have delay divided by 3. So the average delay will end up being the same for the whole system. But because they're chained together, kind of the shape is going to be a little bit more different here. So this blue curve is the standard smooth that we've already learned. That's kind of a toilet tank example. But the smooth 3 is a curve that still they hit in kind of similar spots here, but there's this crossover where this blue one it's sluggish to begin with, it's more sluggish to begin with, but then it picks up and gets faster, and then it rounds off. And what you'll see here is that as the number of this number here increases, then what this is going to turn into is a fixed delay. So higher order smoothing functions allow you to bridge the gap between smoothing delays and fixed delays. Like if this was smooth infinity, it would be a fixed delay of whatever this delay time is. So I think I've got examples of that. Like if I go from smooth 3 to smooth n, then what you can see here is that these are all delaying with an average delay of, or smoothing delay of 2, which since the step rose at 1, that would be 3 seconds. And so you can see they're all kind of intersecting around 3 seconds. And as I increase the number after the smooth, it's kind of bending it, turning it more and more and more into a fixed delay. Because a fixed step delay would just be a step that happens 2 seconds later. So the smooth n, where n is equal to 20, this is like a smooth 20. This smooth 20 is almost vertical, so it looks almost like a fixed delay. So if you want something that's in between a smoothing delay and a fixed delay, you can use these, what they call higher order smoothing functions. So it's a way that you can kind of drop things in and kind of feather these delays. You're like, it's a little too sluggish. The average, I don't want to increase or decrease the average time, so I'm just going to change the shape of the delay. So instead of typing smooth, I'm going to do smooth 3. And that's not quite right either, based on the data I see. So maybe I'll do smooth 20, and so on. So it's a way that you can get from one type of delay to the other. And so this is, roughly 2 second delay. So there's inside Maker and inside Vensim, you'll find that they've got these functions. It's like smooth 3 and delay 3, smooth n and delay 1, smooth and delay 1. And inside, like Moorcroft's text, sometimes he'll use delay functions and smooth functions. There's these things inside Vensim are identical for this class. Once you get into more advanced examples where the delay changes over time, just kind of a weird second order thing where you're saying that it might be, instead of just a plain old 2.5 second delay, at the beginning of the sim, it's a 1 second delay. Later in the sim, it's 2.5. Later in the sim, it's a 5. This is kind of like, imagine a conveyor belt at an airport where it changes its speed. So you go in and it's really going fast, and then over time it kind of goes slow, and some other times it goes fast. When you start getting changing delays, then the behavior of these two functions behave differently. But for this class, we don't really worry about changing delays. So these are like synonyms for each other. So it's a little confusing when you go into Vensim, it's got like a list of functions you can use. You're going to find delay functions and smooth functions, and they're identical. So for this class, you can use either one, and they work the same way. All right, so that's higher order delays. So any questions? That's kind of the extent of the sort of main technical content for today. We got fixed delays, we got smoothing delays, and we got higher order delays that help us get from smoothing delays back to fixed delays somewhere in between, and how to implement them in Vensim and in SiteMaker. Okay, questions online? All right, so announcements, just reminders here. This is lecture E2. Lecture E3 will be Thursday. E4 is a week from today, and that's when your next chapter reading, which is chapter 6. And so we've skipped over chapters 4 and 5, although chapter 4 does have some nice content about delays. So if you're looking for more reading about delays, I recommend skimming through chapter 4. But we're going to jump straight into chapter 6. And so from this point on, we're going to start seeing more examples of how to use stock and flow diagrams to model, epidemics, to model. There's actually an oil example, a global oil example, where we're going to add in Russia at the end. And so it's kind of topical, although this is like more Cold War USSR and, in the breakdown of USSR, not, today's Russia, but you could imagine a similar sort of idea, because we definitely will see the similar pressures we're seeing now reflected in the model that we'll see in the global oil model we'll build coming up here. So then assignment so far, Sunday night, there's this muddiest point, but don't forget there is this assignment E2. It is due Sunday after lecture E5, so that's basically a week from Sunday. So you got, roughly 2 weeks to do this assignment. It's, I think, 3 questions, where the third question is a bonus question, if I remember right. And so you've got lookup tables and delays, and kind of a bonus that kind of mixes those guys, if I remember correctly. Then, yeah, so muddiest point, reading exercise for about a week from now. You've all formed your teams. That's great. Your proposals due this upcoming weekend. So Sunday night after lecture E3, so it's basically this upcoming Sunday, only one group member needs to submit. It's about a page, maybe 2. Look online for details. Feel free to ask me some questions. And that's all I've got for you. So let's close with an attendance question. And if there are any other questions, I'm happy to take them. Otherwise, I'll let you guys out a few minutes early. So attendance question here, let's say, we'll say that a higher order smoothing delay is a mixture between a smoothing delay and a blank. So I said at the end here, a higher order smoothing delay is a blend between a standard smoothing delay and a blank, fill in the blank. So I said that if you've got these different curves, a smoothing delay is going to look like one thing, and as you increase the order of the higher order smoothing delay, it gets steeper and steeper, and the steepest value of the smoothing delay kind of looks like something else. And so the higher order smoothing delays are a mixture of a true smoothing delay, a pure smoothing delay, and something else. So a hint would be the other purest type of delay. And that's all I've got for you. All right, I'll leave the recording on for, actually, I'll go ahead and stop the recording, but if anybody online has any questions, I'll leave the room open. I've got a couple people coming up to me for questions in class, but feel free to, I'll come back here in a second once I handle this question.